First, let's talk about Newtonian gravitation. In Newton's theory, gravity is a force between two mass. As you get closer to a massive body, time curves more. But here's the twist. General relativity is a theory of curved space and curved time. If there are terms modifying the spatial components of the space-time interval, shouldn't we see their effects in planetary and satellite orbits? The answer is yes, but these effects are tiny. Planetary velocities are extremely small compared to the speed of light. Despite this, the first hint that something was wrong with Newtonian gravitation came over a century and a half ago. In 1859, Urbain noticed that the orbit of Mercury couldn't be explained by known physics. The perihelion of Mercury's orbit exhibited an excess rate of precession, only 43 arcseconds per tropical century. This tiny anomaly was a big deal. Leverrier's finding led to a frenzy of searching for a new planet, dubbed Vulcan, within Mercury's orbit. Spoiler alert, no such planet existed. Fast forward to 1916, and Einstein showed that this anomalous precession of Mercury could be explained by the spatial terms in the curvature of spacetime. Einstein's most spectacular prediction was the bending of light around a massive body. Light has a slope of -1 on a spacetime diagram, meaning its movement in space equals its movement in time. In general relativity, the spatial curvature terms predicted a doubling of the bending of light compared to Newtonian predictions. This was confirmed during the 1919 Eddington eclipse expedition, catapulting Einstein to fame. In Newton's theory, the only source of gravitational force is mass. But general relativity identifies several sources of spacetime curvature. These are presented in the stress-energy tensor. The various sources include mass-energy density, momentum density, and the rates of flow of momentum. Is spacetime really curved? Enter Poincaré's conventionalist views. According to Poincaré, the choice between Euclidean and non-Euclidean geometry should be based on economy and simplicity, not on an inherent truth about the universe. A realist might argue that Einstein discovered spacetime to be inherently non-Euclidean. However, a conventionalist would counter that Einstein simply found non-Euclidean geometry more convenient for describing the phenomena he observed. In other words, Einstein's analysis might not necessarily tell us what the geometry of spacetime truly is. So, is it possible to represent general relativity in terms of flat spacetime? Surprisingly, the answer is yes. In the flat spacetime paradigm, matter creates a gravitational field that causes rulers to shrink when turned from circumferential to radial orientation and causes the ticking rates of clocks to dilate. This approach is fully equivalent to the curved spacetime in that both represent the same physical phenomena, but their mathematical formulations differ significantly. Working physicists often switch between curved and flat spacetime techniques depending on the problem at hand. Flat spacetime techniques are particularly useful for approximate calculations in weak gravitational fields, such as those involving gravitational waves. On the other hand, curved spacetime techniques are more suited for analyzing intense gravitational phenomena, like black holes. Let's now venture into an even more mind-bending concept, known as asymptotic symmetries. In special relativity, the symmetry group that governs spacetime is the Poincaré group. This 10-dimensional group includes 3 Lorentz boosts, 3 rotations, and 4 spacetime translations. But what about general relativity? What symmetries might apply when we consider the gravitational fields of the universe? To tackle this, let's imagine observers located far away from all sources of gravitational fields. The initial expectation would be that the asymptotic symmetries of spacetime would simply extend those of flat spacetime. Unlike the finite-dimensional Poincaré group, the infinite-dimensional nature of the BMS group suggests that the kinematics of spacetime can indeed be separated from the dynamics of the gravitational field, at least at spatial infinity. Let us talk about the relativity of simultaneity. Imagine you are standing still, watching 2 events occur at the same time, say a lightning strike in the east and another in the west. From your perspective, these events are simultaneous. But what happens if someone else is moving at a significant fraction of the speed of light? In the realm of special relativity, simultaneity is not absolute. This means that what may appear to be simultaneous events to you may not be simultaneous to someone else moving at a different velocity. This phenomenon is known as the relativity of simultaneity. Events that are simultaneous in one frame are separated by a space-like interval, meaning they cannot influence each other causally. The light cone, which represents the limit of causality, remains invariant across all frames of reference. Non-relativistic classical mechanics treats time as a universal quantity of measurement that is uniform throughout, is separate from space, and is agreed on by all observers. Classical mechanics assumes that time has a constant rate of passage independent of the observer's state of motion or anything external. It assumes that space is Euclidean. It assumes that space follows the geometry of common sense. In the context of special relativity, time cannot be separated from the three dimensions of space because the observed rate at which time passes for an object depends on the object's velocity relative to the observer. General relativity provides an explanation of how gravitational fields can slow the passage of time for an object as seen by an observer outside the field. In ordinary space, a position is specified by three numbers, known as dimensions. In the Cartesian coordinate system, these are often called x, y, and z. A point in spacetime is called an event and requires four numbers to be specified, the three-dimensional location in space plus the position in time. An event is represented by a set of coordinates x, y, z, and t. Spacetime is thus four-dimensional. The path of a particle through spacetime can be considered to be a sequence of events. The series of events can be linked together to form a curve that represents the particle's progress through spacetime. That path is called the particle's worldline. Mathematically, spacetime is a manifold, which is to say, it appears locally flat near each point in the same way that, at small enough scales, the surface of a globe appears to be flat. A scale factor, c, conventionally called the speed of light, relates distances measured in space to distances measured in time. The magnitude of this scale factor, nearly 300,000 kilometers or 190,000 miles in space, being equivalent to 1 second in time, along with the fact that spacetime is a manifold, implies that at ordinary, non-relativistic speeds and at ordinary human-scale distances, there is little that humans might observe that is noticeably different from what they might observe if the world were Euclidean. It was only with the advent of sensitive scientific measurements in the mid-1800s, such as the Fizeau experiment and the Michelson-Morley experiment, that puzzling discrepancies began to be noted between observation versus predictions based on the implicit assumption of Euclidean space. In this idealized case, every point in space has a clock associated with it, and thus the clocks register each event instantly, with no time delay between an event and its recording. A real observer will see a delay between the emission of a signal and its detection due to the speed of light. To synchronize the clocks, in the data reduction following an experiment, the time when a signal is received will be corrected to reflect its actual time, were it to have been recorded by an idealized lattice of clocks. Physicists distinguish between what one measures or observes after one has factored out signal propagation delays versus what one visually sees without such corrections. Failing to understand the difference between what one measures and what one sees is the source of much confusion among students of relativity. Throughout the mid-1800s, scientists were captivated by the mysterious nature of light. Experiments like the Michelson-Morley experiment aimed to understand the propagation of light through a hypothetical medium known as the luminiferous ether. However, the results were perplexing and contradicted the prevailing theories. Enter George Francis Fitzgerald and Hendrik Lorentz, who proposed that objects moving through the ether would contract in the direction of motion, a concept now known as the Lorentz contraction. In 1905, Albert Einstein published his groundbreaking paper on special relativity. By recognizing that the speed of light is constant and that the laws of physics are the same for all observers, Einstein introduced a new way of understanding space and time. Meanwhile, Hermann Minkowski, Einstein's former mathematics professor, was also exploring the implications of these new ideas. In his 1908 lecture, Space and Time, Minkowski introduced the geometric interpretation of spacetime, uniting the concepts of space and time into a single four-dimensional continuum. However, as he developed his theory of general relativity, Einstein realized the profound importance of Minkowski's work. The geometric interpretation of spacetime became a cornerstone of general relativity, allowing Einstein to describe the curvature of spacetime caused by massive objects. In conclusion, the concept of spacetime, from Newton's classical mechanics to Einstein's theory of relativity and Minkowski's four-dimensional continuum, we have come a long way in comprehending the fabric of our cosmos.